We're now going to discuss the curl of a vector field. The first thing that we need to introduce, though, is this del operator. We've seen this operator before when referring to the gradient of a surface function, where fxy is some arbitrary surface, and when we apply this del operator to that scalar surface function, we end up with a vector that is the first partial with respect to x, first partial with respect to y. So now let's isolate this del operator and define it by itself independent of that surface function. And this del operator has meaning when it operates on either a scalar function, which we've already seen with the gradient vector, but it can also operate on a vector field. Now this del operator is called a differential operator because what it does to the either surface function or vector field that it's operating on is that it calculates partial derivatives. So what this del operator did to our surface function was it calculated the first partial of f with respect to x and the first partial of that surface function with respect to y. So now let's talk about the curl of a vector field, and we'll begin by looking at the curl in three-dimensional space. So let's let f at x, y, z be some vector field in R3, where the first partial derivatives of each of the components of that vector field all exist. The curl of f is defined to be this quantity here. But instead of trying to memorize this complicated formula, we could actually pretty easily calculate it by looking at this theoretical determinant. If we take that del operator that we defined just a moment ago and cross that with the vector field components, we end up with this formula for curl. So let's take a look at that. When calculating this cross product, we're going to eliminate the column and row of the I vector. We'll get that I vector then multiplied by the product of the elements along the main diagonal, which will be partial r respect y, minus the product of the elements along the other diagonal, which will be partial q respect to z. And then from that we subtract the j vector times some product. We're going to eliminate the row and column that contains j, and then look at the product of the elements in the main diagonal, which is partial r respect x, minus the product of the elements along the other diagonal, which is going to be partial p respect to z, and then to that we add the k vector times a product. To get that product, we're going to eliminate the row and column that contain k. We start with the product of the elements along the main diagonal, which is partial q respect x, minus the product of the elements in the other diagonal is going to be partial p respect y. And as you can see, that's exactly what we have here. So we can just memorize this bit as our formula for calculating the curl of f. Notice that the output of the curl of f is going to be a vector field. The curl of f is going to depend on an x, y, z ordered triple that we plug into the curl of f vector field function. And each of these domain elements plugged into that curl function is going to give us a corresponding output vector. And again, this was the scenario when we're looking at a three-dimensional vector function and calculating the curl. Now let's consider the curl in two-dimensional space. In R2, we're going to have a two-dimensional vector field with components p and q, and when those first partials of p and q exist, then we can calculate the curl of that vector field, which is then defined to be the partial of q respect x minus the partial of p respect y. And the output of a curl in two dimensions is going to be a scalar quantity. But notice any two-dimensional vector field could be graphed in three dimensions by looking at the vectors only in that xy floor. And so a two-dimensional vector field can be expressed in three dimensions, where we have varying p and q components, but the z component is always 0. This is the same as that two-dimensional vector field in the xy floor. And from this perspective, if we used our 3D formula for calculating this 3D curl, we end up with a 3D vector where the z component of that curl vector field function is partial q respect x minus partial p respect y, which, as you'll notice, the z component of this 3D vector is precisely what we get if we were to calculate that two-dimensional curl. Let's stay in R2 for just a moment and say that if we have a two-dimensional conservative vector field, our test to determine whether or not a 2D vector field was conservative was to look at these two first partials. And if they're equal to each other, we said that that vector field was a conservative vector field. If these two first partials are equal to each other, then that means this curl quantity would turn out to be 0. This then actually leads us to a theorem which says that if we have a conservative vector field, then the curl of that conservative vector field is going to turn out to be 0. And as it turns out, the converse is also true, that if the curl of a vector field is 0, then that vector field must have been conservative. But we should probably make note of the fact that this converse is only true if the domain of our vector field is simply connected, meaning that there are no holes in it. Now let's take a moment to summarize what we've learned about curl and also add a few more things to the list in terms of properties. When we are in two-dimensional space, the curl yields a scalar quantity. If the curl of f is 0, that means that f is a conservative vector field. And if f is a conservative vector field, that would imply that the curl of f will be 0. Now these next properties help us to understand what that scalar quantity actually tells us about the vector field. Remember, the curl of this vector field has an output that is a scalar quantity which depends on the xy ordered pair that we plug into it. If that scalar quantity turns out to be a positive number, then what we'll see is that that vector field is causing counterclockwise rotation around that point. So for example, if we were to see some vector field where we had vectors that looked like this around the ordered pair 3, 0, this would be a scenario where we would see a positive curl output at the point 3, 0. It looks like the rotation is happening counterclockwise around this point, based on the direction of those vectors in the vector field. And so a positive curl represents counterclockwise rotation. If we were to calculate the curl of the vector function and evaluate it at another point, and the curl scalar output turns out to be a negative quantity, this is going to represent clockwise rotation at or near that point. And on a graph, that might look like having vectors in the vector field that are pointing like this around our domain element, which would seem to imply that if we dropped an object in a pool at this point, that object would rotate in a clockwise direction. And finally, if that curl turns out to be 0, then we say that the vector field is irrotational at that point, that we do not get any rotation there. So up here we had a negative curl. When we calculate the curl of a three-dimensional vector field, the output is itself a vector field. Again, we do have the same property that if we have a conservative vector field, then the curl quantity is going to be 0, but this time we call that the 0 vector because the curl of a three-dimensional function is a vector. And conversely, if that curl calculation turns out to be the 0 vector, then we can say that that vector field was a conservative vector field. Again, we have the same property that if the curl of a vector field turns out to be the 0 vector, we don't get rotation at the ordered triple. But if our curl vector output is not the 0 vector, what does that tell us about how an object rotates? Let's consider an arbitrary point in three-dimensional space, but extremely magnified so that we've zoomed way in on it and it looks like a sphere. If we plug this point into our curl, it's going to yield a vector. And that vector is going to be pointing in the direction of the axis of rotation at that point. So here is a vector that could be representing the curl of that vector field evaluated at this particular point. It's pointing in the direction of the axis of rotation. And that rotation is going to follow the right-hand rule. So with the right hand, we put our thumb pointing in the same direction as this vector. And then whatever direction your fingers are curling, when you wrap your fingers back around to your thumb, that's going to be the direction of the rotation at this particular point. And so the curl of a vector field, whether in 2 dimensions or in 3 dimensions, gives us rotational information about that vector field.